Welcome to another lesson on formulae. This is Learning Outcome Part 4 in 3.1 according to the 0620 Chemistry IGCE syllabus. Here's the core content we'll be looking at today. Construct word equations and symbol equations and show how reactants form products, including state symbols. I'll pose this question. Well, can you write an example of a simple word equation and show how these reactants form products? Remember to like and subscribe at the end of this video. Thank you for watching. Achieve your potential with Robert Macbeth. Next slide. Here's a general idea of how you balance equations if you've never come across it before. Start by counting number atoms on both sides of the equation. We'll go into more detail in the next slides. Use coefficients to balance the equation by adjusting the number of molecules or formula units. Remember to balance the atoms one at a time, avoiding changing subscripts. So if you've got the correct chemical formulae, don't change that, you put coefficients in front. That's what that means by this. So if you do your maths, you know that we mean coefficients as a number in front. Here's an example, classic example of the combustion between methane, which is here as a model, and oxygen, which is here. So there's oxygen, and then we get two products formed. One of carbon dioxide, that's a chemical formula. Here's one of water, the classic H2O here. Now, as you know, when we balance these off, when we say start by counting numbers on each side, this left-hand side you can see is called the reactants. So we count off a number of carbons. We've got one here. There's one suggested here. And then the whites represent hydrogen. So there's 1, 2, 3, 4. So we've got 4 hydrogens here. And then we've got 2 oxygen molecules, but you've got 1, 2, 3, 4 oxygen atoms here. Now we go off to the product side, which is over here. We want to see if they balance. So we've got carbon dioxide here, C, 1 carbon here, 1 carbon there. We've got 2 oxygens here. There's 1, there's 2. And then we get 2 waters formed, H2Os. You can see here. But if we count off the number of hydrogens, you've got 1, 2, 3, 4, which is that. And then you've got 1, 2 oxygens each for the different water molecules. So if we go to the next step, we're counting the total number of atoms on each side. We can see we've got 4 carbons, 1 carbon, 4 hydrogens, and 4 oxygens. And here, when we add them all up, we have the same number of carbons, 1 carbon, 4 hydrogens, 4 oxygens. And because of this wonderful law of conservation of mass, it obeys that with left-hand side reactants, the number of type of each atom balances lovely with the number and type of each atom on the product side. Okay, so we're looking at different types of reactions that you'll come across. These are the typical ones that you'll come across in your course. In experimental work, we've got synthesis, containing 2 or more substances to form a single product. So here we've got a simple one called reactant A and reactant B to form product C. Remember, these on the left-hand side are called reactants, and on the right-hand side of this arrow are called products. Here we've got an example, sodium plus chlorine, and we get the compound C known as sodium chloride. Decomposition, as it suggests in biology and chemistry, it means to break down into its simpler constituent elements. Here's an example. A is broken down into B plus C. It could be more, but in this case we only got 2. So we've got the reactant here. We've only got 1 reactant. And here we've got 2 products A and B. Sorry, 2 products B and C. Typical classic example is when you heat up calcium carbonate, it breaks down into calcium oxide and carbon dioxide. Next general equation we'll have a look at is a single replacement reaction. It occurs when one element replaces another element in the compound. So here's a diagram representation. You've got reactants A plus BC and then you can see that C goes with A, and then B stages itself to form a new product called AC, and then B, the element. So it's a single replacement reaction when one element, in this case A and C, replace one another. And we get the double displacement reaction, double replacement reaction, sorry. Two compounds exchange elements to form two new compounds. Double replacement reaction here, you can see A plus B plus C plus D. You can see these swap over, where D goes to A and then B goes to C, and we form these new products AD and CB. It doesn't matter which way they're around, but they are new products, thus the same. This is called a double replacement reaction, where two compounds exchange elements within their compound to form two new compounds, in this case AD and CB. Here's another reaction you'll come across called atypical, happens every day, combustion reaction. It's a reaction where a reactant reacts with oxygen, usually producing carbon dioxide and water. So we've got A plus B gives you C plus D, but we've got B has to be oxygen for a combustion reaction, and it usually produces these two products under certain conditions, carbon dioxide and water, usually in excess oxygen. So we have a lot amount of oxygen, and we usually get those two products only. Here's an example: methane plus oxygen gives you carbon dioxide and water as a word equation. Next slide. Okay, writing equations here, a little bit more detail. I've highlighted these. Writing reactants on the left-hand side, so we're going to practice doing that. Products on the right, and we're separated by an arrow. We use appropriate symbols and formulas for each compound. They have to be correct. Okay, symbols. Remember from the previous slides, you have to name those reactants and products correctly, or else it all goes to pot and you don't get the correct balanced chemical reaction or equation in this case. So you balance by adjusting the coefficients. Remember, you don't change the reactants or product formula. They should be correct in the first place. And we ensure that conservation of mass and charge are conserved, i.e. number of charges on the left-hand side and the right-hand side. In this case, reactants and product equals also the number and type of atoms on the left-hand side compared to the right-hand side. We use these typical state symbols. S stands for solid, L stands for liquid, G stands for gas, AQ from the Italians, aqua or aqueous means the substance dissolved in water to form a solution, aqueous. Note, always double check your charges and valencies of the elements and ions when writing names and formula. Remember, they have to be correct, or else your balanced chemical equation will not work out in the first place. So it's very important that you get the chemical subscripts and symbol formulae correct first before you start writing your fully balanced chemical equations.